este o mare plăcere să fiu la Timișoara pentru a treia oară în mai puțin de o lună. Am fost la conferința Smart Diaspora, am fost la o lansare de carte săptămâna trecută și acum, iată, a treia oară, deja mă consider timișoran, știu toate cafenelele, toate librăriile, e o plăcere. Am să țin totuși conferința în limba engleză, așa am căzut de acord cu organizatorii, așa că, hello ladies and gentlemen, I'm going to start with a love story between humans and computers. It started in 1950 with a paper by Alan Turing. Alan Turing was in charge with a small team at the Physics National Laboratory in London, in United Kingdom. And they created a big machine, half the size of this room, that was able to perform additions and subtractions and multiplications and divisions way faster than any human. If you've seen the movie The Imitation Game, it was about deciphering the code of 𝑚, the machine used by the Germans to communicate. So that was the first time when computers helped humans. It's interesting that Turing, in his paper, asked the question, can machines think? And he even designed a test, the Turing test, some of you might know, and estimated that it will take maybe 50 years before a program will pass the Turing test. It did pass. He was wrong by about 15 years. The test was passed in 2014. But then, in the 70s, there was a big transformation in the way computers assisted humans in research, in innovation, and so on. We were able now to create documents, to store information. Instead of paper, we had huge and ugly 8-inch floppy disks, then smaller floppy disks, then DVDs, then USB thumb drives that can store more than 1 terabyte of information. Another change I'm glad to say that it was a good part of my career in science, was related to high-performance computer. Huge machines, terabytes, petabytes. We are going to exascale now. Programs that are able to simulate natural phenomena that can help us understand nature and predict properties of physical and chemical systems. I would say that as we were approaching the new millennium, computers began to provide information. They became a source of knowledge. We could Google stuff, we could search through find information in Wikipedia. There were machines such as this one, Watson, created by IBM, at the time, and maybe even today, one of the most knowledgeable entity you can have. But is Watson an intelligent computer? It will be for you to decide. I'm proposing that now we are in the middle of another transformation. Machines can think, can advise us. Computers and intelligent software are part of the research teams, are able to suggest solutions, to propose decisions to humans, and even more, can make decisions by themselves. Isn't that frightening that a machine will perhaps replace many of us, myself first of all, and take over some of the tasks of our professions? I'm going to use 2 examples to connect artificial intelligence to reality, to what happens in the labs, in research, in science and industry. First example is from science. We were looking at hafnium oxide, hafnia, also called. a material that was introduced by Intel in 1997 to add, to complement, if you want, the properties of silicon oxide for memory in computers. But we wanted to understand how arrangements of atoms in hafnia are related to the properties of these materials, especially the electric constant and other properties. Can we understand this connection between atoms, their arrangement, and the properties of the material? Here is an example of how the experiment provided the basic information. So I'm talking about using artificial intelligence in connection with experimental work in the lab in reality. We created a very small piece of hafnia and levitated that using ultrasounds, such that it was in a containerless environment. It didn't touch any container, any wall. And we used X-ray diffraction and neutron diffraction to understand what are the positions of each atom in the lattice, and determine, perhaps, the input parameters for computer simulations, the ones that I mentioned. In this case, ab initio molecular dynamics and density functional theory, quantum mechanics. Now, getting into the details of artificial intelligence components, I don't know if anybody presented that, but at a conference where almost every presentation has an AI in the title, I thought maybe that wasn't necessary. I'm going to talk about machine learning as one of the main components, deep learning, which is machine learning based on neural networks. And within that, there are three classes of algorithms. One of them is supervised learning, where the data is labeled. In this example, you see density, raw versus temperature. We use the algorithm to analyze the data from experiment and from computer simulations and create a model that relates these two properties. And then to your left, you'll see a second class of machine learning algorithm. It's called unsupervised learning. The data is not labeled. The algorithm doesn't care what kind of what these points represent. But we do. All the points, the green ones, the yellow ones, the red ones, are actually configurations, atomic configurations, arrangements of atoms. And we train the algorithm to recognize these configurations and to group them based on the way they influence the property of the material. I'll say a little bit more in the second example. So you see, these are very different way of programming compared to what I did in undergrad at the university. All the Fortran, all the decision trees, if x smaller than 2, then add y to z, are not there anymore. These algorithms are not pre-programmed to make decisions. They learn from examples how to make decisions, pretty much like humans, like students. All of us, throughout our entire life, learn from bad examples, from good examples, how to decide. And depending on our education, we make good or bad decisions. It's no different with the algorithms in machine learning, in deep learning. We have to educate them well, train them well. What is also important, and I think represents perhaps the most powerful element of the impact of AI on science, is the fact that after training the algorithm, after evaluating their predictions, it will keep learning. The more experimental data we provided, the more results of the high-performance computer simulations we provided, the better the model became. It would learn through our results, but also through the predictions it made itself. What we got out of this was the tremendous speed up in predicting properties of materials and relating them through the atomic positions. 10 times. At Los Alamos, it took me 2 weeks to set up an interatomic potential, that is the force between, is related to the force between atoms. 2 weeks, 2 weeks. Now we can do it in 2 days. And the results of the predictions are similar in terms of accuracy and precision to quantum mechanics, to density functional theory, which is regarded as the ground truth in this area. The second example uses different components of artificial intelligence. Computer vision, the ability of analyzing images, which is something that we as humans are doing very well. This is a chemical process, flame spray pyrolysis. We throw a lot of chemicals in a flame and get out a powder with a specific size distribution. So I'll invite you to evaluate what do you think? Is this flame stable or unstable? Or you can't tell. We have a technologist now, a human, who does that. The technologist will spend hours monitoring this in the lab or through a camera. Wouldn't it be nice to have a software that can do the same? So we thought, let's have a project and design an intelligent software that can observe and monitor and maybe even make decisions regarding the stability of this process, of this chemical process. And we use 2 approaches. One of them that I mentioned before, supervised learning. We spend a lot of time labeling various features of a flame, much like we do in our brain, right? The size, the intensity of the color, the shape. And then, using convolutional neural networks, trained these algorithms and have it make predictions about the stability. Here is how it works. Is that what happens in your brain when you watch these flames? Maybe it is, right? I hope my mind is simpler. I don't think I account for all these features, but the algorithm does. And it does really well in predicting stability and instability of flames. But it takes a lot of work. We have to train it, give instructions, show it thousands of video clips with hundreds of thousands of images. It's a lot of work. So how about the other type of algorithm? Unsupervised learning. We take all the information, all those video clips, all those images, use principal component analysis to represent that information in 2 coordinates, and then ask the algorithm to simply group these points into 3 areas: stable, unstable, and uncertain. You may think, anybody can do this, it's not that hard, right? But what if you have 3 coordinates? What if you have 4 or 12? You cannot even imagine how that space look like, not to mention grouping them. What if there are 10,000 points? So the machine can do far better than the human in this respect, and in fact made a classification. So I need your input. If we assume in an outrageous and arrogant way that humans are always right, how do you think these 2 classes of algorithms did in evaluating stability and instability of the flames? So who thinks the supervised one, the one with all the features, all the aspects of the flame that was trained on thousands of images, did better? How close to 100% being the humans, what percentage do you think of success had the algorithm? Anybody? 40. Anybody else? 60. 80. 90. Very good. How about the other one? The one that required less training, that will just group things kind of looking at the video clips and look, okay, these are stable, these are not stable, very little work. What percentage compared to humans do you think that was? 93, 95. Anybody else? 23. Here is the result. So the supervised learning algorithm, the one that required a lot of training, did almost as well as a human. The other one required less training, but did really well, 73%. Is it acceptable to you, is it acceptable to the scientific and engineering community to use this intelligent software to help a human technologist, or maybe even better, to replace it, to replace him or her? Is that a bad thing, to have a technologist lose their job in favor of this software? What are they going to do after that? No, the good side of this is a story with happy ending. The technologist embraced this tool, is using it now to monitor the flame day and night, and he's doing something else. His mind is more creative now, imagining new experiments, thinking of how to develop this technology further. Some considerations about how artificial intelligence is making a tremendous impact on science and on technology. These tools augment our brain. They make us smarter. They make us more creative. They have advantages and disadvantages. As I said, they might displace some people from their jobs. It is concerning that at some point intelligent software will communicate, will form a community, that they will make decisions, and with or without our consent will take action. Isn't that scary? No, I'm not scared. I'm an optimist. I think we can control this technology. We can have it as a partner, as a team member. We thought of adding the code to the list of authors of the public publications and decided not to, because it didn't show signs of creativity. It did a lot of work better and faster than we could, but there was no new idea coming from the intelligent software. Not to mention that doesn't have a personality, cannot tell jokes, you cannot go out for a beer with the software. So there are many drawbacks, but there are many advantages too. Another aspect is that we don't fully understand how these algorithms make such good predictions. There is no analytical relationship anymore. And for a physicist like me, that is really saddening. I like to understand things. I like to make a connection between what predictions say is going to happen and the physics and the chemistry of the system. I would also say that it is often the case that people blame artificial intelligence for all kinds of negative aspects. I don't think that is fair. We train these algorithms. We educate them for what, a couple of weeks, a couple of months. How long have I've been trained for 24 years in the formal way, and my entire life by my family, my friends. I learn continuously. I learn from you today. I believe that the responsibility for using artificial intelligence in a good way lays with us, with the humans. We have the power to make it truly a partner, a member of our research teams, and maybe to add this software to patents and to scientific articles. I think that's going to happen by 2035, and I hope to be back here in Timișoara to confirm that and to read an article that has as a co-author artificial intelligence.